Assalamualaikum warahmatullahi wabarakatuh. My name is Farah from Space Science Center 8, PRIN. Today I will present about our research in ITB with Professor Taufik Hidayat about continuum study on Uranus at the millimeter submillimeter wavelength with ALMA. To begin with, let me explain about the research background. Why did I study Uranus using ALMA? First, Uranus is a very unique solar system body, but it is also the least understood even when compared to the twin Neptune. Uranus has extreme rotational axis tilted around 97 degrees, and the luminosity of Uranus is the lowest as the internal heat almost zero. We can see from the internal structure, which remains unclear with so many questions from the core until the outermost part. We can also see the internal magnetic field and magnetosphere of Uranus is asymmetric. Above all, the only spacecraft to visit remains Voyager 2 in a flyby mission, picturing the pale blue featureless object in the visible light without any spectacular cloud bands or storm during solstice. And presently, the ice giant type is happen to be the most typical in exoplanet detection. It makes Uranus become more important because we need better understanding about kind of ice giant in our solar system as local laboratory. However, thanks to technology of telescope, both in space and ground, Uranus can continue to be observed, particularly on equator during equinox. This dark spot observed in infrared with Keck telescope in Hawaii, and the bright spot seen with Hubble Space Telescope. And this high contrast image is from Keck and Gemini telescope, revealing so many features on the equator. With radio wavelength itself, Molter 2020 also took image of Uranus with ALMA and also plotted the continuum model that I want to achieve as well in this study. Then why ALMA? ALMA is a very sensitive radio interferometry in the world. It has very wide band of observation windows and high resolution, and ALMA frequently observe Uranus from time to time as the calibration target. And well, this is our purpose. With the abundance of ALMA data, we will reconstruct some images of Uranus to obtain a flux contour features along with the orientation. Then the second purpose is to understand the distribution of flux density as well as the brightness temperature over some frequencies on ALMA band. On this data and method section, let me start with the brief basic principle of interferometer by limit diffraction equation. If we want to improve the angular resolution, we need a larger diameter for sure. The longest interferometry baseline can replace the diameter of the dish. For example, in this picture, with the longer distance between these two elements, the resolution can be smaller. Many radio telescopes in the world use this technique. One of them is ALMA, Atacama Large Millimeter Submillimeter Array, which consists of 66 antennas located in Chile. With that dry climate and very high place, it can cover large frequency range, and the longest baseline up to 60 kilometers can reach the resolution until 0.004 per second. The ALMA can be the data can be downloaded from the archive, and this is the query from to be filled with our criteria. To tune the large datasets, we use the download script under Linux. The program we use named CASA, Common Astronomy Software Application by McMullen et al. 2007. As it's seen on the flowchart, after the data import, it will continue process called flagging, then calibration before move on to the process, in this case, imaging or convolution. And the top panel here is a dirty image of Uranus from ALMA that will appear once we start the convolution process. Start with masking, the iterative, and then iteratively subtracting until it looks uniform between residual noise and masked image. After that, we can end the process and finally obtain the clean image which contains a model and residual image. The result of a flux value or S can also be converted to the brightness temperature with this equation. We can look at the planetary data system NASA to know the Uranus ephemeris and to calculate the theta. Other parameters such as Uranus orientation for analyzing the image could also be seen from the PDS NASA. Finally, this is the result. The data we had mostly from band 3 and 6. Following for band 7, 4, and 8, with total size about 5 terabytes. Of all the project downloaded, about half were successfully calibrated, resulting 110 observation data. and some of them were concat or merged, resulting 78 data points. This number is what suitable enough for our research. Moreover, we also had one project targeting Uranus as a scientific object. After all the cleaning process, we had a diameter of Uranus between this range. Each image has a various beam width. With the Uranus diameter of 3.5 arcsecond, they are divided into the three categories: well-resolved, marginally resolved, and unresolved. It appears that the resolved data is less than unresolved, showing by this pie chart and this plot. More dot above Uranus diameter is presented in red dashed line about 3.5 arcsecond. It's more than the resolved one. Below is the table that includes the most well-resolved observation data represented from each band and observation time. There are some parameters we obtain, such as the diameter of array, longest baseline, date, time, and frequency. The next section summarizes the conclusion result of continuum image from previous table. The frequency band are written in the lower right corner of each image, and the table per band here contain unit and relative contour level, also beam in arcsecond. Observation beam is also displayed in the lower left corner here. Meanwhile, this right axis is a flux scale in Jansky per beam. The lighter color indicates the higher flux density number. Well, except for the first and the last image, it seems that the contour profile are quite sharp, indicating the smaller angle resolution means those images are well resolved. And these slides only show a higher resolution image along with the orientation geometry from PDS NASA. We can see that the best contour image observed by Molter et al. 2020 as the only observation with Uranus as a scientific target in a band 3, 4, and 6. These images show the bright color of higher flux density that represent the Uranus bright pole here and here, and is seen from the geometric image below. It appears that the Uranus in 2012 was observed at the equator. As the year progressed to 2080, it seemed the turn to be towards the point of view, the poles. Furthermore, both resolved and not resolved data on the flux values were plotted to with the continuum curve of Uranus. This plot describes the distribution of flux density over various ALMA wavelength range divided at some band from 3 to 8, as you can see here. In this plot, it appears that the flux value in Jansky tends to be higher as the frequency band increase. The increase is also accompanied by the higher uncertainty, because the higher of observation band, the instrument error will be higher and also have an atmospheric effect. From the dense curve, it can be converted into the brightness temperature curve with this equation, as I explained on the method. If the density curve have no correction to the ephemeris, this plot consider them with the calculation of the diameter divided by the distance in kilometer that varies during some observation periods. And the brightness temperature here is decreased with the frequency, as would be expected for a planet with dense atmosphere like Uranus, with a higher temperature at lower altitudes. On the curve, we get an expected decreased profile for higher frequency, because the result is quite appropriate, because it spans between the Uranus temperature equilibrium about 50 Kelvin. The slightly spread out point of the curve are due to the seasonal fluctuation of Uranus, which cause changes in the direction of view of the bright poles, and the high error value in the lower band is due to the larger telescope beam width. This quite big error is roughly estimated from the calibration error, which generally can reach to 10%. This result in a certain range is in line with a Uranus continuum model plotted by Molter et al. 2012. Well, I think that's all my presentation. This is the discussion and summary. After all, we hope that in the absence of instrument dedicated to monitor Uranus, these images and continuum plot can contribute to Uranus study that can be achieved with ALMA data, even though mostly only as a calibrator. And below is the acknowledgement, as I would like to thank ALMA, because this research makes use of 59 ALMA projects listed on the paper. And also to Lapan Scholarship, because this research is part of my thesis project in astronomy magister program in ITB. And here are my references. Any discussion and comments are welcome. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.